Hi everyone, welcome to this LM seminar today. We are happy to have Frank from Imperial College talking about this nice topic of non-equilibrium topological band theory. So let's welcome.
Thank you so much. Okay, thank you all for coming here. And I wanted to make this into like some kind of very pedagogical introduction. So I'm not going to show you a lot of stuff. Usually in talks, I kind of, after 5 minutes, I stop paying attention or I don't understand the talk anymore. So I'm only showing you the first 5 minutes today. And then the rest of the time we have to fill by, if you ask me questions or so, you can help me out. Otherwise, we'll be done pretty soon. But I wanted to talk to you about this topic. It sounds a bit technical, but I will try to introduce it really slowly. So non-equilibrium band topology. By non-equilibrium, let's first talk about non-Hermitian. So nowadays, there's like this big literature that goes on about non-Hermitian Hamiltonians, and it's supposed to model systems with loss and gain. So when you have lifetimes, or when you pump your system, then you can talk about, for example, like quasi-particles. Let's say have a lifetime, they decay in time, and so you could model that with some non-Hermitian Hamiltonian. For example, imagine your Hamiltonian for a single particle is just minus I gamma, where gamma is some real constant. Then naively, at least, your time evolution would be e to the minus IHT, would be e to the minus gamma t, right? And so that would decay exponentially in time. So you would model that, for example, you would say, oh, here's a particle which with a wave function decaying exponentially in time means that the probability that the particle is still there decays exponentially in time. And there's now a few results on trying to make sense of band topology. So you might have heard of band topology in the context of Berry phases, Chern numbers, topological invariants, whole connectivity is quantized in 2D and so on. People have now generalized all of this to non-Hermitian Hamiltonians. So to the general case where H is not equal to H dagger. So from now on, I'll just call this the non-Hermitian case, so NH in short. Now, what's interesting is that there's new topological invariants you can get from that. And yes?
Why do you relate the non-equilibrium with the non-Hermitian?
Because it's loss and gain is non-equilibrium. So we don't talk about a ground state anymore or any like static property. Yes, definitely. And actually, so in general, non-equilibrium, we could think of like open quantum systems. Let's say you have loss and gain, or you have like some jump operators in the general Lindblad equation treatment of open quantum systems. And in some limits, you can show this corresponds to a non-Hermitian Hamiltonian, which I'll talk about actually later. So it's true that you can have non-equilibrium with Hermitian Hamiltonians, but then usually you need to have some coupling to an environment to have a non-equilibrium system, right? Because otherwise it's described by equilibrium statistical mechanics. Or you need to look at time evolution. And so here I'm taking the path where I'm basically looking at coupling at an environment in an effective way. In a way, the coupling has already been taken into account, and I've ended up with a non-Hermitian Hamiltonian as a consequence.
All right, so it's the static Hamiltonians you're looking at, not time dependent.
Yeah, but
so
non-Hermitian.
Not to have equilibrium, you need.
Yeah, but actually, I'm gonna say later that things don't make physical sense so much as we would like them. I'm just saying, now I'm kind of giving you in the first part a little review of like what people care about in this field. And then I'm basically gonna give a little argument why I think, at least for me, it doesn't make a lot of physical sense if you try to apply it to a many-body quantum system. And then at the end, we'll go to full Lindblad open quantum systems, which do make sense. So I'm saying non-Hermitian doesn't make sense, but there's lots of nice math results. And the hope is that we can save them somehow, that there's some lifeboat we can build for these beautiful math results, that they don't just go all the way down the drain of like being just beautiful math results, but they actually have some physics in them. And for that, we need to go to then the Lindblad description of open quantum systems. Okay, any other questions so far? Then let me show you the simplest non-Hermitian topological invariant. And actually, things are much simpler than in the Hermitian case. So whoever doesn't know about the Chern number or Berry phase, you don't need to know about it. Things get much, much simpler. So non-Hermitian band topology. Just consider a 1D model. And in undergrad, we start with this 1D chain, right? And we have a hopping strength T. And then hermiticity requires if you have a hopping T to the right, then you also have a hopping T to the left. So always like you have this reciprocal hopping T to the right, T to the left. Now, that means your Bloch Hamiltonian, right? When you do a Fourier transform, hopping to the right gives you a factor e to the ik because you're going one step to the right. And then you go one step to the left, and both of them are the same in the Hermitian limit. So you get this cosine dispersion, 2t cosine k. Right, and that's the undergrad result. You have this cosine dispersion. It's a 1D lattice. And in T, usually you choose it to be negative so that you have the band minimum at k equals 0. But now to make this non-Hermitian, the simplest thing you could do is you just drop the hopping to the left. So let's just get rid of that. So I'm dropping all the hoppings to the left. That means I'm dropping the second part here. And now I'm just left with t to the ik. And that's the simplest non-Hermitian Hamiltonian you could think of in 1D. And if you look at the spectrum of that Hamiltonian in the complex plane, so now it's non-Hermitian, so its spectrum in general is complex, it just makes a circle, right? And it makes a circle that has some winding to it because as we go around the Brillouin zone, momentum space, as we tune k from 0 to 2 pi, my spectrum goes counterclockwise in the complex plane. So when we talk about topological invariants, we always need some notion of a gap. We need some notion of adiabaticity. If I keep a gap open, then that means I'm doing a smooth deformation. If I close the gap, that's a phase transition. So you could introduce a new notion of gap, which is called a point gap, which I'll define, for example, here at the origin, that we are not allowed to close. So we can't have any states right at the origin in the complex plane. That could be one condition for a gap. You could also consider, like if I have some other complex spectrum, which has spectrum here and here, then you could introduce something like a line gap, a whole line through the complex plane, like this line or that line. Oh, sorry, like that line, which doesn't have any states. But as soon as you have a line gap, I can always make these spectra real without closing the line gap, so that I end up with a purely real spectrum. And so if I do that, then I have some spectrum here. Whoop. Oh, sorry. So I have some spectrum here and here because I've put them all to the real line without closing that line gap. So it's essentially a Hermitian type of gap. I'm back to my Hermitian system with a real spectrum. So a line gap is fundamentally different from a point gap. For a point gap, imagine I want to make the spectrum real by pushing these energies down onto the real line. That will give me a gapless spectrum. It will close the gap. So this is not related adiabatically to any Hermitian insulator. That's the big difference. Line gaps are basically Hermitian insulators. So all the invariants you have for Hermitian insulators, like the Berry phase, the Chern number, you can define for a non-Hermitian Hamiltonian with line gaps. But for a point gap, you have a new classification, and that needs to be worked out. There's this big paper called Symmetry and Topology in Non-Hermitian Physics, where they work out that there's actually 38 different symmetry classes instead of the usual 10-fold way. There's now 38. But we don't need to know about that. Let me just go on talk about that model. But before I do that, do you have any question about the notion of gaps? All we need now is the point gap.
So what do you plot here in the K space?
Just the full spectrum, because I can't really do a 3D plot well. So this here is k equals 0, for example, and this over here is k equal pi. So I'm going around the circle as I go through K space.
Yeah, it's K. K can be real.
K can only be real. Yeah. But my spectrum is complex because my spectrum is e to the ik. So I'm plotting the spectrum, so the eigenvalues of this Hamiltonian for all possible choices of k. Yeah, they can either make some point gaps, so they can go around some point where there's no eigenvalues, or they can make line gaps. Or those are at least two useful ways of like characterizing these spectra. And I'm saying the line gap is kind of similar to a Hermitian type of gap, because I can then collapse the spectrum onto the real line without closing the line gap. But I can't do the same for the point gap.
In this case, you don't care about translations like that.
That would be fine. I can define the point gap anywhere else. I could define it up here or so.
You just added the
Yeah, that's fine. That's like in the Hermitian case, it would be like shifting your Fermi energy. Yeah. Okay. So we can write down a topological invariant for the point gap, which is the winding number. And the winding number is very simple. It's just counting how many times do we wind around this gap here. So how many times, it must be an integer number because I have a gap at the origin, right? So I can calculate how many times I go around, and in order to change that, I would have to drag my spectrum across the origin. So I would have to close that point gap. So it must be always an integer, and then in general is given by this equation, 1/2 pi integral of decay, and then it's d by decay arg, so the argument of the complex number of the determinant of h of k. So in our case up here, h of k is e to the I k. The argument is k. So d by dk of k is 1. So I'll just get 2 pi divided by 2 pi is 1 in our case. In general, this is always some integer. If it's -1, we go around the other way. We go around clockwise instead of counterclockwise. But it's very easy to see that this invariant cannot change without closing this line gap up here. Like this line, sorry, this point gap. So this point gap, it protects this invariant. It makes it quantized. So now you see why it's simpler than Hermitian topology, because I'm not using any eigenstates. In Hermitian topology, like Berry phase or Chern number, it uses the Bloch eigenstates, the eigenstates of h of k. But here I'm just using h of k itself. So for the experts, it's more similar to the Hermitian invariants associated with chiral symmetry, where you use just parts of the Hamiltonian. So what's cool about this invariant is, like, right now, all I'm saying is this is one way to characterize 1D non-Hermitian Hamiltonians. But the cool thing is it has a physical consequence. So let's consider the model we had from before.
But can't you,
yes.
Don't you use this winding number also when you have SSH chain?
Exactly. So just to remember, in the SSH model, your Hermitian Hamiltonian looks like this, for example. And then you define this winding number as the winding number of the top right corner. And then it's exactly the same winding number. Yeah, and that's chiral. So that you can do because your Hamiltonian anticommutes with chiral symmetry, which is this matrix in the SSH. So this anticommutator vanishes. So it's true that for systems, there's actually a one-to-one mapping of Hermitian systems with chiral symmetry to non-Hermitian systems without any symmetry. Okay.
In the chiral symmetry case, the point gap is always at the origin.
Yeah, in that case, zero energy is really special because of the symmetry.
But in the non-Hermitian case,
Yes.
this
Yeah. Exactly. Yeah. So that's more. It's more general, but it's just a shift. It's just an overall shift.
Yeah. But the overall shift matters, right? Because it tell you if you have exponential decays or exponential growths.
That's true. Physically, it matters. Here, I'm just completely agnostic to the physics so far. I'm just playing games with matrices. Yeah, but you're right. In general, it matters. Okay. If there's no more questions, then what's cool about this is, let's have a look at our model again in real space. So the model had only hopping to the right. So if I make an edge, I just terminate my system here, then everything will pile up. So my wave functions, if you look at your eigenstates, they'll all pile up at the boundary. They'll all be exponentially localized at the boundary. And that's called the non-Hermitian effect. So consider this for a moment. It's a dramatic phenomenon. All we've done is we've changed the boundary conditions. But normally, if we change the boundary conditions in a Hermitian system, you only get order 1 states, like maybe some edge states, or you don't. But you don't change your bulk spectrum. You don't change your bulk plane waves. You still have Bloch plane waves, even in open boundary conditions. Here, we do open boundary conditions. Suddenly, instead of plane waves, I'll have exponentially localized states at every point in the spectrum. All my eigenstates will be localized at the boundary. So it's a very drastic phenomenon that only works because for non-Hermitian matrices, you don't have certain inequalities called Weil inequalities that usually prevent you from having a drastic change in your eigenvalues when you change your matrix just a little bit. Like there's this theorem, if you change your matrix by order epsilon, your eigenvalues can only change by order epsilon, basically. That's only true for Hermitian matrices. For a non-Hermitian matrix, you can change your matrix by order epsilon, suddenly your matrix changes by order 1, like here. So it's pretty drastic. And what's cool is you can show that whenever your winding number up here is non-zero, then you must have a non-Hermitian skin effect. So there's, in a sense, you can compare this to a bulk boundary correspondence. Like in a Hermitian case, if the Chern number is non-zero, you have chiral edge states. Here, if the winding number is non-zero, then you have a skin effect. And you can prove that. So that's a pretty beautiful paper. It's called a topological origin of the non-Hermitian skin effect, where they show that. And it's perfectly rigorous. And that really shows you that the winding number is important because it gives you this drastic behavior in open boundary conditions. And now we're back to what we know and love. And usually in band topology, we have a bulk classification, and we have a set of boundary, like protected boundary phenomena, like edge states, gapless edge states, and so on. And there's a correspondence between the two. Now we have something like that bulk boundary correspondence also for non-Hermitian systems. So that's the first part that I wanted to show you. That's like what's cool about non-Hermitian band topology. Do you have any questions about that part? The next step is why it's not so great after all.
Can you formulate it more?
So the rigorous way to formulate it. Yeah, but the rigorous way is you need something like in the Hermitian case, like an edge termination. Then it's rigorous, like some boundary to the vacuum. Yeah, so it's the same as like in the Hermitian case. So the statement is whenever you have a winding number, then you have a skin effect. There is a more rigorous way of resolving the Z invariant. I've kind of glossed over this. I glossed over the fact that it's Z, whereas the presence of a skin effect seems to be just a Z2. It just seems to be either you have a skin effect or you don't. So there's a way to resolve the Z, which I don't want to go into. It's a bit fidgety. But the basic idea is spectrum winds in momentum space, then in real space, everything will pile up at the boundary. And that you can show rigorously. Like, you don't even need to do the real space calculation. You can just predict it from seeing the winding in momentum space. Everyone happy? Okay. So now it's a little paradox time. So non-Hermitian problems. Let me call it non-Hermitian problems. And actually, I'm open to suggestions. Maybe you have a way to solve this paradox. I just didn't find a nice way, so I kind of moved on from non-Hermitian. But I've tried to do this for a many-body Hamiltonian, right? So in a many-body system, you might want to write down, for example, the Hamiltonian from before, just a simple decay, where gamma is some real quantity. And then in many-body, we have second quantized operators. So I want to write down, for example, a C dagger C. And to make it really many-body, I need at least 2 particles. So I'll add another one in for good measure. So I might want to write down a Hamiltonian that looks like that, where C and C dagger are fermionic creation and annihilation operators. So Ci, Cj, dagger are delta Ij. They satisfy these canonical anti-commutation relations. And Ci, Cj is 0. And the reason I want to do that is that even for a non-interacting model, it is at our own peril that we neglect the many-body perspective. For example, in a Chern insulator, like a non-Hermitian topological insulator that has chiral edge states, the coolest result about these systems is that the whole connectivity is quantized. You only see that in the many-body wave function, even though it's a non-interacting system. So the many-body perspective is important, even though there's no interactions. We need to be able to make sense of things from a many-body point of view and look at the many-body ground state and fill up our states and so on. And I want to make sense of that also now for the non-Hermitian case, where so far we just talked about the single particle matrices, like the Bloch Hamiltonian I showed you was just a single particle concept. So let's just ask the question, can you make sense of this? And I ran into an obstacle even for this Hamiltonian. Like, we don't even need to look at the hopping model from before, but let's look at this matrix. It basically tells us that particle 1 and particle 2 both decay at the same rate gamma. So what happens if we introduce two states? I have an initial state phi of 0 that I'll define as just particle 1 is occupied. So C dagger 1 acting on the vacuum. So just to remember, the vacuum is defined by the equation that is annihilated by all annihilation operators. So this state here is really just a state where you only have a single particle, particle 1. And I also want to look at another state where I have both particles occupied. And these are normalized states so far. Everything's fine so far. But if I look at the time evolution, my naive non-Hermitian time evolution, if I put in a t here, is e to the minus iht times phi 0, which is equal to e to the minus gamma t times 1 plus 0, right? Because this is the particle number for particle operator for particle 1. That's clearly equal to 1 in phi 0. Particle 2 does not exist in the state, so particle number operator is 0. So I'll just get 1 plus 0 done here. So that time evolution.
How we are doing the evolution? Where does that come from?
Right. I'm just assuming a naive time evolution. I'm saying let's pretend this was the rule. And you're exactly right. We have to actually think about what physically it means to have, where it came from, right? We have to know where this non-Hermitian description came from. But let me assure you, a great many papers just assume this evolution naively and do not question it.
Yeah,
so exactly. So I just want to show you a problem that comes by assuming that, and then a solution of how to make sense of it.
I mean, if you're saying you have a non-Hermitian Hamiltonian, this is the only thing. This is what makes sense, right? You're solving this Schrödinger equation with the non-Hermitian Hamiltonian. You could say that it doesn't make sense to say you have one.
Yeah. Well, you could, for example, argue that you should renormalize your state after every time step. But then you will actually get rid of the time evolution altogether. So you don't see the decay anymore at all if you renormalize.
This is what people do in quantum optics. Right?
Yeah. But for example, there's papers that that look at Lieb-Robinson bounds and non-Hermitian Hamiltonians, and they assume this kind of time evolution. Okay, so this is just equal to e to the minus gamma t, right, times c dagger 0, c dagger 1, 0. So just to continue this calculation, I can also do the same for size of t. And now I'll get e to the minus gamma t times 1 plus 1, right? Because both particle 1 and particle 2 are occupied. So all I get is this factor of 2, e to the minus 2 gamma t. C dagger 1, C dagger 2, acting on the vacuum. So the problem with that is now if I calculate something like an expectation value, for example, I could calculate the expectation value of particle number 1. You see where the problem comes in. That guy goes like e to the minus 2 gamma t, because I have e to the minus gamma t from the left and from the right, and they don't cancel because it's real. It's a real number now. Normally this kind of stuff cancels because you have a phase factor that cancels from left and right and a Bryant cat. And now if I take the very same operator in this different state, psi of t, and remember the operator is just particle number of particle 1. So it doesn't care about particle 2. for all our purposes, particle 2 could be in the Andromeda galaxy. I get e to the minus 4 gamma t. So just by including another particle, which does not interact, if you look at this Hamiltonian, there's no interaction between 1 and 2, just independent. But by including a second particle, I've made my first particle decay twice as fast. And so actually there's some papers that say Lieb-Robinson bounds are violated in non-Hermitian Hamiltonians, and they sell it as a feature. But I actually think this is a deeply problematic statement because there's not even, well, maybe they didn't look at a Hamiltonian where there's really no interaction, but here there's actually 0 interaction between the two. So how can a particle that's over there influence my particle over here? Do you have any ideas maybe? I didn't find a good way to make sense of it, but maybe there's some.
I mean, it's true, like, kind of, it's just some number you're multiplying the observable.
Mm-hmm.
Right? So, I mean, calling it a violation of the Robinson bounds, but like, it's not non-local, right? It's just like, you always get some overall factor of like e to the minus 2.
But as soon as you start taking superpositions of these guys, it won't just be an overall factor anymore. So it's really more tricky than just, you can't just cancel it out. So the only way I could make sense of this, and this is like what people in the open quantum systems community knew all along, is that whenever you have an open quantum system description, which means you have a quantum system and you have an environment, and you trace out the environment, and you do post-selection, something called post-selection, which is like you do a bunch of measurements and only a specific outcome of measurements, only a specific trajectory you keep, and everything else you throw away. Then you indeed have evolution by a non-Hermitian Hamiltonian. That makes sense. So what this tells us is that we are measuring particle 1 in the state where we have post-selected on particle 2 being present. So we've post-selected on the quantum trajectory in which particle 2 is still here because we're using psi and not phi. So that means we would have to go over to the Andromeda galaxy, check if particle 2 is still there, and then come back, and that's the effect. That's how the non-locality comes in. And then we keep the measurement, and then we calculate expectation values. But you see that this runs into trouble pretty quickly. If we have n particles, then we have to constantly check the particle number, do measurements, and the probability that not any of them will decay will go down exponentially, or the probability for any path, any post-selected state will go down exponentially. So this is not a feasible thing to do for a many-body system.
So, I mean, like, so should that locality be related to unitarity or something?
No, actually here you have measurements, so technically it's not unitary, but it's still local because...
Exactly. That's what I'm saying, that non-Hermitian theory shouldn't necessarily, we don't expect them to be local.
I don't necessarily expect them to be local, but if they do not interact, if they have two particles that don't seem to interact, then I expect that particles not to know about each other. Right. So that's what's like, it's not so, it's not as like there's a tiny interaction and maybe there's a non-local effect, but here there's really zero interaction between the two particles.
Right, but did we expect to be local? You know, that's my question. Or we will expect a unitary theory to be local, maybe a classical theory to be local, but this is a hybrid between the two. So
yeah. So maybe I would be willing to give up locality, but I wouldn't be so happy about a theory that has two particles suddenly affect each other that don't interact.
That's right, but all these statements are making sense in a unitary theory.
Yeah.
See? So here it's,
yeah.
Would we expect it, or it's a completely different thing?
Yeah. Yeah, I think the fundamental problem we have is that we do not really know how this came about physically in the first place. We just posited some non-Hermitian Hamiltonian and see how far we got.
And it's exactly how you get non-Hermitian theories is by post-selecting, but like doing some projection, right? So it makes perfect sense that you get this type of thing.
Yeah, and the problem is that you can't really do for a many-body. So I think post-selection in a condensed matter setting is just very hard. There's this Google experiment that probably Zlatko knows best about. But I don't know. Do you know how many qubits they did post-selection on? It can't be like maybe 20 qubits or so. I don't know. But you can't do it for 30 probably. Like you run into this problem, this exponential increase. So that's just saying that there's like, you really have to imagine there's like thousands of papers on non-Hermitian band topology that are kind of, let's just say, ontologically naive as to what it means physically. But there's beautiful math and like bulk boundary correspondence and classification of the type that I've showed you before. Like, for example, with the winding number implying the skin effect and so on. So there's like, this has been done not just in the 1D case that I've showed here, but this has been done in all 38 symmetry classes in all dimensions and so on, has been generalized. There's really a lot of work on this. So my goal here is now to just like make sense of it in a physically reasonable setting and see how much of it we can save. So that's part number 3. We go to the full Lindblad equation. So just to remind you, in the Lindblad setting, we don't talk about the state, the pure state, but we talk about the density matrix, which I'll call rho. So in the pure state case, the density matrix would be just cat psi bra psi. And the reason we do that is that physically, whenever you have a system that's coupled to an environment, then it will not remain in a pure state if you trace over the environment. So all you can do is you can write down an equation of motion for your density matrix rho, which in general reads like you have some term that looks like your previous unitary evolution, commutator with h, that's just Heisenberg equation of motion. But then you also have some term that looks like a term that couples you to an environment. And these are called jump operators, JM. And then there's a JM, dagger, JM. So the first time you look at it, it looks a bit weird, this equation. But you can check, for example, that it preserves the norm of the density matrix. And you can check that it has some nice properties, like it preserves the fact that the density matrix eigenvalues are probabilities, classical probabilities, and it keeps it Hermitian and so on. And these jump operators, I only want to look at 2 cases here, where so either this is equal to something like Cm. So maybe let me use proportional, because in general there's some proportionality constants. Cm, this is loss. I only have annihilation operators, so I lose particles. Or I have C dagger M, and that's gain. So for the experts, that means I have something called weak U1 symmetry, which basically precludes any terms like C plus C dagger, like superconducting terms. I don't want pairing terms. And now the fact that we'll use is that this equation we can rewrite in the following way. I can rewrite it very suggestively by introducing some new H tilde. And remember, this H here is purely Hermitian, right? So all my coupling to the environment comes in via J. Does not reside in H so far. This is like a different way of looking at open quantum systems. But I can rewrite this as some H tilde where I have something like almost a commutator, but I have to account for the fact that H tilde now is non-Hermitian. And what I've gained by that is I've gotten rid of the second part in the jump up term, and I only retain the first part. And then H tilde is defined as my original Hermitian H. And then I have a plus, or sorry, a minus I over 2. Actually, sorry, this I should be a plus I. And then Jm, well, sum over m, I guess. Jm dagger Jm. So I've kind of made my Hamiltonian H tilde non-Hermitian because of this term that multiplies the I. It's non-Hermitian in general because J dagger J is always Hermitian. So I times that is perfectly anti-Hermitian, but then I'm adding to it a Hermitian matrix. So this is in general non-Hermitian. And what I've gained is I've kind of reduced the complexity of my second term here. I've kind of packaged the dynamics into a non-Hermitian evolution plus something called the jump term. And you see why this is the jump term, because physically what it does is this, the Jm, for example, in the case of loss or gain, it increases or reduces the number of particles in my density matrix row, whereas the non-Hermitian evolution, it preserves the number of particles. So it doesn't switch between, it doesn't jump between sectors of different particle number. So now you see how non-Hermitian evolution comes about. If we just keep continuous measurements going on, like we do some quantum Zeno measurements of the particle number, that effectively sets this term to 0. And then we're left with non-Hermitian evolution. So this is just non-Hermitian evolution. So,
measure and forget.
yeah, so if you just keep doing measurements, then we can never jump. And then we get rid of this term over here. And so here we have an equation that we know makes sense physically, because this has actually been measured in the lab. This has been like, is well motivated. And you can actually show that Lieb-Robinson bounds hold. So locality holds for this Lindblad equation. But we have an equation where we can go to a limit when we set these jump terms to 0 by doing continuous measurements that recovers our non-Hermitian formalism from before. So now we can do a meaningful comparison of the non-Hermitian evolution that we get after post-selection with the full Lindblad evolution of the density matrix. Okay, maybe before I go on, because this was a bit technical, do you have any questions about that?
The density matrix formalism is in preserved causality, and while the other form does not.
So the other form has this problem of non-locality, for example, from before.
But this one preserves locality.
Yeah, and it preserves the trace of the density matrix, so there's no weird decay of any probability.
Hardwired in the master equation. While the other doesn't preserve.
Yeah. So I'm saying this equation, there's no question about its physical interpretation. This one is fine, is legit. The other one, we have all of these questions of how to make sense of it.
Not obvious you can write this hopping.
It's not obvious, but you can. Yeah. Yeah, you have to do a bit of work, because you basically want to write the hopping Hamiltonian in 2 parts, in a Hermitian part and an anti-Hermitian part. And you can do that. What? Right, all you get is some terms on the diagonal in addition, so you shift your entire spectrum by some, yeah. Then you can do it. So the hopping only to the right, you would build out of some Hermitian Hamiltonian that has hopping going both ways, and then an anti-Hermitian part that has hopping only, like has hopping asymmetric, like going to the right with a different prefactor than to the left, that cancels out the first one. Okay. Any other questions so far? So then let me just look at the winding number again. So before we define this 1D winding number, we can use that for H tilde as well, right? We can define winding number. Let me call that W of non-Hermitian, because it's the winding number of the non-Hermitian Hamiltonian H tilde. Or I could call it W post-selected, so post for post-selected. H tilde is a perfectly well-defined non-Hermitian Hamiltonian. So that is a good winding number, and I can actually build models where I have a point gap. So in general, this is Z quantized. This is like some integer for a 1D system. So yeah, I actually don't have time, I think, to go through the model, but there's a way to make a model. But in general, you can think of just thinking of this guy is some non-Hermitian Hamiltonian, so it will have some form of H tilde. You can define some momentum space Bloch Hamiltonian, H tilde K, and that you can use to define the winding number. Let's go up here using just that equation where replace the H of K by H tilde of K. And that winding number would tell me about the skin effect after post-selection, like we had before. So we have all the results from before, just like in this different kind of physical interpretation of doing full open quantum dynamics plus post-selection. But we said we don't want to do post-selection because it's physically very hard. For a many-body system, it becomes impossible. So let's just file this away for now. We also need to define a winding number for the full Lindbladian. And what do I mean by that? I mean the full Lindblad equation up here, which includes the jump term, which is something that kind of describes systems without post-selection, just like generic open quantum systems. So how can I define a winding number for that full object if I have all of these weird jump terms flying around? The problem is I can't really write this as some Hamiltonian, as some matrix, naively at least, because I have the jump term here coming from the left and from the right. So what we do is we do this thing called vectorization, where we turn this thing into a vector. So basically you can imagine that by as just taking your density matrix rows, and then you just write all the rows one after each other to make a very long vector. You just flatten the matrix into a huge vector. So you made an n by n, maybe I shouldn't use n, but let's use L for length in 1D, L by L density matrix. And I should say in the many body case, this is 2 to the L by 2 to the L density matrix row. You turn this into a 2 to the L squared, so 4 to the L dimensional vector that I'll denote by row, and then I'll use this double cat because I want to, my normal cat, I want to reserve for normal state vectors, and so my double cat is for matrices that have been vectorized.
No, row, okay.
Yeah, I'm sorry. You know, I studied ancient Greek in high school, but I took over the physics row. But yeah, what is it? Is it like that? That's the ancient Greek row. Sorry, I took over the physicist's way of writing row. Okay. So the Lindblad equation, and we're almost done, I'm promising. Lindblad equation turns into I vector row dot time derivative of this vector is equal to some Lindbladian super operator vector row. And I've defined this big matrix L hat, which kind of takes into account this full Lindblad equation up here. We see that this equation is linear in row. So after the flattening, this must correspond to some matrix acting on my super vector, my row cat. And this is this matrix L hat. Right, maybe I should we do double hat? Why not? L double hat, because it's an operator acting on matrices, on density matrices. So all you need to know is that I can do this because my original equation is linear in row. So I can always package things into a matrix equation by flattening. And now there's this beautiful result due to Prosen, which goes under the somewhat pretentious name, but I love it, of third quantization. Who of you has heard of third quantization? So in third quantization, we introduce operators that create creation operators. And because we want to like write down the super operator L, right, which acts on matrices, so it acts on operators. We know that our basis of operators in a many-body system we can span by C and C dagger, the creation and annihilation operators. So now in order to act on that basis, we want operators that create creation operators, destroy creation operators, create annihilation operators, and destroy annihilation operators. And Prosen has done it for us. And the final result is that we can write this big super operator in the following form. We can write it in an eigenmode basis, where we have some eigenvalues lambda alpha, and then we have eigenoperators B dagger alpha B alpha, which satisfy something called the almost canonical commutation or anti-commutation relations. B alpha B beta is 0, which is B alpha prime, B beta prime. But then we have the usual B alpha, B beta prime is delta alpha beta. And importantly, B alpha is not equal to B alpha prime dagger. Like if we had a Hermitian L hat, then indeed those would be just daggers of each other, like prime would be equal to dagger. But in general, L hat is a non-Hermitian operator. It's a big non-Hermitian matrix. So it's not just, it doesn't just diagonalize in terms of these canonical fermions, but it actually diagonalizes in terms of these pseudo operators. Because L hat, even though it came from a well-defined Lindblad equation, which preserves the trace and everything, but L hat itself is a non-Hermitian operator. L hat dagger is not equal to L hat in general. So all you can do is you can write it like this. But that's good enough for us, because now you can define the steady state as, for example, it's just a state that's annihilated by, so I'll call it cat steady.
So it's B alpha at the left diagonal, B alpha prime on the left, and then B alpha.
Exactly. That's what it is. Yeah. You take left and right eigenvectors. So it's basically a bi-orthogonal decomposition of this. So I can define my steady state by the fact that it's annihilated by all my B alphas. Because then if we go up to the Lindblad equation, that tells me that rho dot is 0. So it doesn't change. So that's the steady state right there. It's the state that has a density matrix that does not change in time. So my steady state becomes the vacuum of these fermions, B alpha. And now I can define my relaxation modes, which are like the excitations. Relaxation modes. So these are kind of the eigenstates that if you initialize your system in them, then they will decay to the steady state. They will look like excitations like B dagger alpha and so on, acting on the steady state. So it's the usual game of ladder operators where I build my spectrum by defining a vacuum and then I act with ladder operators on the vacuum. And I can build a whole spectrum out of this. Okay, so this is a long story. I wanted to show you this because I wanted to make contact between the Lindblad equation and a band structure. Now we have these lambda alphas to play with from up here, which are like the eigenvalues. They decay, they tell you how fast your things decay back to the steady state. So they're generally non-Hermitian. And if they are complex, then that means there's decay. So in general, in your complex plane, real part, imaginary part, you can prove they only exist in this plane down here. They all have negative imaginary part, which is required for the system to decay into the steady state. You don't want any exponential growth. And you can show that rigorously, actually. So your lambda alphas, in general, they define a band structure. For example, if you have translational symmetry, then they are lambda alpha of k. Everything depends on plane wave momentum k. So that allows you to finally, that's the final result. So you can define a winding number, which I'll call W Lind for Lindblad, which is also some integer. So the long story is, or the short story, I should say, is we have a winding number that comes from the post-selected Hamiltonian. And now I've defined a winding number via this long process of doing third quantization and writing the Lindbladian operator in terms of an eigenmode decomposition. I managed to define a winding number for the full Lindblad equation that is basically coming from vectorizing the Lindblad equation. And now I want to compare the two, because this tells me about the skin effect without post-selection and the topological invariant without post-selection. So in what you can prove, and this is now in the paper, so I can't, the proof takes like 2 lines or so. It's not very hard. You can show that this winding number of the Lindblad system has the following 2 limits. It is equal to the winding number of the post-selected system, whenever you have only loss. So gain is 0. And it's equal to the opposite winding number whenever you have loss is 0, whenever you have only gain. Which means that in general, if you have a post-selector dynamics that has a skin effect and has a winding number, then you can build a system where you have a phase transition. Like in general, you have, like, let's say you have mostly gain, mostly loss. Here, your winding number for the Lindblad system is for example, +1. Here, your winding number for your Lindblad system is -1. And there's a phase transition. So there's this phase transition. So basically here you have a skin effect to the left of your system. Here you have a skin effect to the right of your system. In between, you have a phase transition. And what's interesting is this phase transition, it's invisible after post-selection, because after post-selection, the winding number is equal. So it's completely different from, like, there's this big community nowadays that looks at measurement-induced phase transitions. And it's a kind of phase transition they have after post-selection. You can't see it without post-selection. Here's an example of a phase transition that you can see only without post-selection. You can only see it in the full open quantum dynamics. You can't see it in the non-Hermitian post-selector dynamics. And so just to give you, like, to finish up, I want to give you a physical intuition for why that works. Let's say you have loss only. And we have post-selector dynamics that I'll indicate with a little arrow that goes to the right. So winding number is positive. My steady state, if I have only loss, is the vacuum, because everything decays. So my excitations, which are basically characterized by these operators B, which make my band structure, which define the lambda alphas, my excitations now are given by particles, little density excitations, then move to the right. So at time t equals 0, I put in a particle. Then at time t equal, let's just say larger than 0, that particle will have moved under post-selector dynamics to the right. And then, of course, it also decays by the jump term. It decays back to the vacuum. If I have gain only, then it's the opposite. So I still have, in post-selection, I still have movement to the right. But now my steady state is the fully occupied state. So now you see why, if I make an excitation, let me just prepare this. If I make an excitation up here at t equals 0, that would be by making a hole. So I kind of make a little drop in the density over here. Then that, under post-selector dynamics, my particles move to the right, so that hole effectively moves to the left. So it's t larger 0, I have a skin effect in the opposite direction. That's why the skin effect changes. Now that seems incredibly trivial, right? But what's cool about this is, in the general case where you have both gain and loss, let's say you have mostly gain, just a little bit of loss. Now you can also, in addition to making holes, you can also make little particles. Naively, they should move to the right. But because of the winding number can't just change this continuously. It's still non-zero. So it will still move to the left, and that's super non-intuitive. That's something that's dictated just by the winding number. So even when, for example, gain, loss are both non-zero, but gain is much larger than loss, or just in general larger than loss in a simple model, then it's still true that all excitations, no matter if they are of particle or hole type, go left. So that's super surprising, and it took us a while to make sense of in the microscopic models. Like, you can look at the numerics and it works, but when you want to understand what's happening microscopically, you have to do some more work. And it kind of relies on the fact that actually what we are doing by making a particle in the gain-only case or gain-dominant case is we are reducing the probability for making a hole. And that's why it still goes the right way, but it looks like a particle because we are reducing the classical probability in the mixture of the density matrix of making a hole. But that's a bit too technical for you right now. All we need right now is that the winding number it's quantized. So if I make a tiny change, if I just change my parameters like loss or gains just ever so slightly, my winding number can't just change discontinuously because it's quantized. It's still the same number. So everything must still go the same way because of the bulk boundary correspondence. My skin effect is still in the same edge. Okay, so that's it. And if you want to read more, please have a look at the paper. And thank you very much for your attention.
So you said there's this correspondence between these non-Hermitian models and the high-level Hermitian models.
Yeah.
That, like, I mean, is it obviously the level of the Lindblad? Because it seems like you have like a H and a H dagger, right?
So
it looks like if you when you vectorize.